So why don't you think about this now? So is this a spontaneous reaction at 25 degrees? And what is the, if it would be, now let's see, delta G naught, if it's 1 atmosphere, okay, but you have this at 25 degrees, you have 1 atmosphere of steam at 25 degrees, would it make more steam or would the steam condense into water? That's the question you have to ask yourself, okay? And many of you have it right. And the K is simple. So if you have water there, there's a very small partial pressure of water on top of it. So the equilibrium, so this is actually only the function of the partial pressure of the gas, the equilibrium constant. And the partial pressure of the gas, anybody knows what the partial pressure of water at this temperature is? Yes, exactly. Good. Why don't you discuss it with each other? That's room temperature, exactly. So it can't hold 1 atmosphere of pressure, okay? At 100 degrees, it holds that 1 atmosphere of pressure. It's very complex, though very simple. Once you understand it, that's the problem. Like with everything, once you understand it, it sounds simple. See, there are nice colors here. Great. Okay, all right. Didn't I green click this before? Did I? I think I did. Okay. So you have a glass of water sitting here. It has 300 of an atmosphere of water vapor on top. That's the equilibrium, okay? And the equilibrium always has the 300 atmospheres of water vapor on top. So the K 300 of an atmosphere is smaller than 1, isn't it? Okay, so K is smaller than 1. This is right. So now, is that in equilibrium? Is delta G, would that be in equilibrium? Delta G naught. Delta G naught is 1 atmosphere of water vapor on top of that solution of water, on top of that water at 25 degrees. At 25 degrees, the water vapor does not come out of it at 1 atmosphere. It comes at 300 of an atmosphere out of it, okay? So it will condense into the water until it's 300 of an atmosphere, and then you're in equilibrium, but this delta G is larger than 0, okay? It will not go in this direction by itself. It will go in this direction. Delta G naught is larger than 0. This is the definition of delta G naught. That tricks you here. Oh, that was all the answer, okay? I think I talked long enough about this. We have delta G is delta H naught at standard state minus T times delta S. You know that very well now, and we have derived all this. And then we said, this is minus R times ln K. We had here, this here we derived here, delta G naught is minus RT times ln K. And we say, okay, this was before, delta G is this here, but we know this is minus RT ln K. Why don't we put that in here? Minus RT ln K. And now we have a relation between K, the temperature, the enthalpy, the standard state enthalpy, and the standard state entropy change, okay? So now let's do a trick. I want to say ln K equals, and I take this, divide this by minus RT, is minus delta H divided by RT, minus gives plus, is minus T times delta S divided by RT. I can cancel the T. I have delta S divided by R. That looks like this then, okay? And so I took this out because I wanted, this looks like a linear equation. I plot ln K, that's my Y. The X is 1 over T. What do I get then? This is Y equals mx plus B, right? So this is my intercept here in this equation, and this is my slope here. And this is minus delta H not divided by R. So if I plot ln K over 1 over T here, so the temperature you measure the equilibrium constant, for example, at a series of different temperatures. You just let it go to the temperature, you have your reaction, you measure the concentration of the product, the concentration of the product, the concentration of the product, the concentration of the reactants, you measure those, and then you can calculate your K, all right? With this, you put this in here, and you get, you plot this against the temperature, you have measured the temperature when you determine your K, you get the delta H not here, and more importantly, you get the delta change in entropy. This is very difficult to determine the change in entropy. You can count it, can count the molecules, but this is not such a good idea. So this is a way to get the change in entropy, for example, and so how would that look like? That would be what kind of a reaction would it be? Remember, we had just defined earlier K as a function of T. If I increase T in an exothermic reaction, that is, we have said that the temperature is a product. With this, it goes, the K gets smaller as I increase the temperature. Now, ln K would be this slope here. So exothermic, this has to be negative. That's a positive slope, but this is negative delta H over R here. So with this, I can get from the slope, I can get here my delta H, and this would be negative, delta H naught. And where would be my delta S over R? Anybody? That's the intercept here, okay? And the delta S, in this case, that would be a positive. See, that is no, I don't know. No, it's not necessarily positive. That's delta S over R, okay? So now, if I have an endothermic reaction, so heat, and this is K over T again here, endothermic heat is now a reactant. So if I increase the temperature, I make more and more products. With this, the K becomes larger with increasing temperature. And that means here, the endothermic reaction, if I have this over 1 over T, that would be, delta H has to be positive. This is a negative slope. This is minus delta H over R, so that will give you delta H as H naught as a positive. And delta S is, again, a positive number. It is delta S over R, so you divide it by R, you multiply it by R, you have your delta S naught. So the free energy, and this is what this essentially explains again, this is our Van't Hoff equation. It's called Van't Hoff equation. It's used the temperature dependence of the equilibrium constant, essentially. And this is delta G naught equals delta H naught minus T times delta S. And I just explained to you all these things, how this is, and there it is now written for you again. If delta G is endothermic, it goes this way, and the intercept is here delta H naught, okay? So that would be endothermic, that must be positive, so it has to intercept in the positive. If it's negative, it would have to intercept here, okay? If it's exothermic. And the slope gives you what? That gives you minus delta S, okay? Because you plot it over T is minus delta S, so delta S is the opposite of this. And this would be ln K over 1 over T, and I just explained it to you. The delta H would be delta S over R would be here, and the slope would be minus delta H naught over R, okay? Now, the intercept is delta S over R, and the slope is minus delta H over R. This is just simple analysis of slopes. Of course, you don't need to really do the slopes anymore. If you have one of this TI 5 million, you just put your numbers in there and put the put the derivatives of those, and then immediately you get these numbers out of there. First of all, you need to know how to operate your calculator, and second, you need to know what the relations are, really, the mathematical relations. In chemistry, it's always nice. In the old days, they didn't have these fancy calculators, and so this helps also. So they had to do these kind of relations. They were plotting the stuff and get these as the slopes and as the intercepts. And this, of course, helps you understand this whole problem and the whole issues a little bit better if you see it as linearized equations. Okay, not necessarily if you're a wizard with your calculator and know a little bit of math. You don't have to do this kind of stuff. You get it right out of your calculator. All right. So now we have these different possibilities here. We have delta H is positive and delta S is negative. So that would be the system's orders more, and it's endothermic. So delta G would be looking like this here. Okay. Delta G would be the intercept. The intercept is delta H. That should be positive. And delta S minus delta S is the slope here. Okay. So that is a positive slope because delta S is negative in this case. Now ln K would be looking like this here. Your delta H. What is ln K? What is your intercept? Is delta S over R. So delta S over R has to be negative. So it has to be here. That's the intercept in this case. You see that? That's the intercept. And your slope is what? Is minus delta H over R. And your slope is positive. So that would be a negative slope in this case. I'm sorry. Your delta H is positive. So the slope has to be negative because it's minus. All right. And then you can play with. You have both of them negative here. So where would that be? Delta H naught should be negative. That would be the intercept. It has to intercept somewhere here, right? Okay. And delta S is negative, so it would have to go somewhere like this here. Okay. And this one, delta H is negative. So where would it have to go? Delta H is negative. Let's see. That would go where? Delta H is negative. No, this is the intercept is here. The intercept is here, delta S over R, this will be plotting 1 over t. So the intercept would be here, okay, that would be negative. And delta H over R is minus delta H over R, so this has to be positive in this case. And there are several other cases where you have delta H is positive and delta S is positive. You need to play with this in order to understand this, but it's a simple relationship. We have done this before in other occasions where we went through all the possible cases, and you can see this here. You have delta H naught is negative and delta S naught is positive, so the entropy increases. Here the entropy increases. This is exothermic, and this is endothermic, and you come to this. Now let's do an experiment where we see a reaction where the change is a change of entropy and enthalpy, and let's have a little bit of fun with this. So we have here a compound, if you could put the camera on it, please. This is ammonium dichromate, if I understand it right. That's ammonium dichromate, isn't it? Okay, that's the red compound. And what Karen will do now, she will make a wick to get it started, and because to overcome the activation energy. And then let's see what happens to this good thing. And you can watch the entropy change, and you can watch the enthalpy change. Okay, and you tell me which way it changed and how the diagram would look like. Okay, which one would that be? Okay, we can have the lights off, please. And a little closer, 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 closer. Closer, please. Closer. Right here. Oh, you have a little volcano. You have a little volcano here. Let's hear it. You hear it? A little volcano all by itself, you know. That's in special effects. That's how they used to do this in the old days in the silent movies. And you remember Godzilla? Okay. Yeah, that is. Godzilla. So that's how they used to do that. Yeah, closer, 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 closer. There's our volcano. Look at that. Huh? So now you know what the entropy does, and you know what the enthalpy does, okay? This is a beautiful volcano here. It makes quite a mess, actually. And so it's spewing. I just was in Hawaii. I didn't see the volcano because I've seen it, the lava flow, many years ago. And so once you've seen it, it's fine. All right? And so that's special effects here. Chem 1A special effects a la Karen. All right, give her a hand. All right, so what happened? Beautiful volcano. And we're all covered with ash here now. And so what happened here? Which one was it? Was it this one, this one, this one, or this one? Who was this one? What was delta H? Delta H was endothermic or exothermic? Exothermic, very good. So you got it started and then it went on by itself. Okay, and now did it get less ordered or more ordered? So it got more disordered. What is delta S then? S naught. It's positive. So this was this here. Okay, so delta S is negative, S is positive, and delta H is negative. This would be, if you plot here 1 over t, that would be the plot for this, and delta G versus t would be the plot for that. Okay, so that was a little excursion into the silent movies. And now I'd like to ask you the following. You remember we had this iodine here, and the iodine equilibrium, we had solid there, and the equilibrium was just depending on the partial pressure. Okay, and so it was at room temperature, and there was some vaporization going on, and the vaporization itself, it wasn't vaporizing everything at room temperature. There was still some stuff left, is there? There was some solid left. So you can say something about the heat of vaporization of iodine. And now compare this heat of vaporization now when we had solid CO2 up here. And the CO2 at room temperature relatively fast, evaporated to gaseous CO2. So what can you say about the heat of vaporization on this one compared to the iodine? So this one, just the room temperature was enough to completely vaporize. With iodine, it wasn't. I point here because it was standing here. With iodine, it wasn't enough. So which one has the higher heat of vaporization? Was it CO2 or was that iodine? That's the first part of the equation that you have to ask yourself. And now you have, in both cases, you have a solid going to a gas, a solid going to a gas. So you look at the entropy, you have solid and you have gas. Okay. It really doesn't matter what kind of solid, what kind of gas you have. A solid is relatively ordered. The gas is quite disordered. So what is the entropy change for that? And if you compare the entropy change, is it different or is it about the same? So now think about this question here. We have ln k versus 1 over t. That gives you here delta S over R, gives you the intercept, and the slope is, I shouldn't be telling you this. Anyhow, and so which is the corresponding plot for CO2 solid to CO2 gas? So this is the plot when you have ln k versus 1 over t for iodine. And now I want to know, if you want to plot this in yellow, would it be this plot, or this plot? Let's think about this by yourself, please. I gave you all the information, actually. So the first thing is, what can you say about change in entropy for both systems? Then you know where to start that plot. Can you all see that panel here? This panel, can you all see it, read it? You can't read it? Let's put it up there. Please. Can you read it now? It's the right top panel. You were shaking your head, that meant you couldn't read it? Or were you disagreeing with your neighbor? Okay, good, thank you. some of you have part of the concept. Some of you have it right, and some of you have it totally wrong. Okay? So, the concept of entropy, quite a few understand the concept of entropy, so that's you're starting out properly. But then you have to compare the heat of vaporization for CO2 with the heat of vaporization for iodine. So which one has a larger heat of vaporization? So how would that, so I'm asking about the one which has a smaller heat of vaporization. That's the one you have to plot. How would that slope be? Okay? Why don't you discuss it with each other, please, and see if you can crack that conundrum here. Okay, I want to solve that still, so I might cut it a little short. I can start out also the next time with this, but I'd like to solve it today. All right, can I close it? Everybody click in, please. We need a couple more. Everybody in? One more. One more, come on. Everybody in. Come on, I gotta get it done here. Okay, yes, you're going in the right direction. That means the entropy change. They are both solids to gas, okay? The entropy, this is a sublimation. So the entropy change is about the same. So it starts at the same point. So this one and this one, because the entropy, the intercept is delta S of R, and so it gets higher in entropy, so it's positive, this or that. But this one was the slope for this here. So if you use this here, then the heat of vaporization would have to be higher, which is not right, because the room temperature for CO2 was enough to completely evaporate it. For iodine, it wasn't. But this is the right answer, and there it is, because the heat of vaporization is smaller. Okay, I see you on Friday. Thank you. Difficult, very difficult.